Yellowstone National Park is home to many natural wonders, but it is also home to several dangerous situations. Throughout the last 150 years, visitors have died as a result of encounters with wild animals, exposure to noxious gases, hypothermia, lightning strikes, being hit by falling trees, falls, drownings, accidental shootings, stove explosions, and murder. The authorities were forced to close the park after a park ranger indicated that something was going on inside. What has just happened, and why is this place closing? In this video, we'll take a look at the Yellowstone National Park's chilling discovery that was made inside. The most common cause of death in Yellowstone is a tie at 12 for motor vehicle crashes and heart attacks, according to an assessment of both natural and unnatural causes. This may sound terrifying, but nature may be the most destructive force in Yellowstone. The possibility of a catastrophic disaster of unprecedented proportions makes the eruption of Yellowstone's supervolcano one of the most feared events in recent history. Despite the fact that many people are unaware of the dangers it poses, it appears to be one of the most realistic threats to the majority of life on Earth, with the potential to lead to human extinction. The theory that the volcano will only erupt in the next 100,000 years is fading, and scientists who previously thought Yellowstone was a dormant volcano are reconsidering. According to new research, the Yellowstone National Park supervolcano has a much larger magma reservoir beneath the caldera than scientists previously thought. Furthermore, according to a paper published Thursday in Science, the newly discovered lava is flowing at shallow depths that fueled previous eruptions. Researchers used seismic tomography to map the seismic wave speed beneath the Yellowstone volcano. According to Ross McGuire, an assistant professor at the University of Illinois, Urbana Department, Campaigns of Geology, and the study's author, a 3D modeling of seismic waveforms measures the volume of the melt and make assumptions about how the melt is distributed in the subsurface in Yellowstone's magma reservoir. We discovered that Yellowstone's crustal magma reservoir probably contains more melt than previously thought, McGuire said, adding that there is up to 20% melt at shallow depths. Previous research suggested that the partial melt fraction was between 5% and 15%, according to McGuire. According to Kerry M. Cooper, professor and the chair of the University of California, Davis's Department of Earth and Planetary Scientists, the Yellowstone magma reservoir is more like a snow cone, with a solid component and a liquid component, than a big tank of magma with accumulation all in one body. Cooper believes the findings indicate that there may be some relatively small to moderate-sized bodies of magma beneath Yellowstone that could be mobilized and expelled. Yellowstone is well known for its potential for catastrophic explosive eruptions, according to McGuire, but that is not the most common type of eruption in the park. They'd be similar in size to what happened in very recent Yellowstone history, when a series of lava flows filled the most recent caldera after the most recently really large eruption, she said. Despite the new discovery, the scientists believe that an eruption is unlikely to occur anytime soon. Yellowstone shows no signs of increased volcanic unrest, according to McGuire. This really doesn't change the hazard assessment at all, because we already knew that. And we already knew that this was the recent activity, Cooper explained. We knew that was the most likely type of activity to occur next. However, determining how much magma is beneath the surface and where it is located is critical for assessing the hazards of volcanic eruption, and continued monitoring of the subsurface is necessary to provide a clear picture if the situation begins to dramatically change, according to the researchers. Furthermore, the US government closely monitors Yellowstone. Cooper mentioned the US Geological Survey and the Yellowstone Volcano Observatory. Yellowstone National Park's geysers and fumaroles are among the most famous and visited geological features on the planet. Millions of visitors visit the park each year to marvel at Old Faithful's towering eruptions. Artists paint pots, bubbling mud cauldrons, grand prismatic springs, crystal clear water and iridescent colors, and mammoth hot springs, stacked travertine terraces. Those who have visited the park may have wondered, where does all the hot water come from? A study co-authored by Virginia Tech's W. Stephen Holbrook and colleagues from the US, the Danish Geological Survey, and Aarhus University provides stunning subsurface images that help to answer that question. The researchers created images of Yellowstone's subsurface plumbing system using geophysical data collected from a helicopter. The method identifies features with unusual electrical and magnetic properties, which indicate hydrothermal alteration. The combination of high electrical conductivity and low magnetization is like a fingerprint of hydrothermal activity that shows up very clear in the data, said Holbrook, a geophysics professor and the head of the Department of Geosciences in the College of Science at Virginia Tech. Essentially, the method is a hydrothermal pathway detector. Images from the study show that the park's geology has a significant impact on its hot springs. Hot hydrothermal fluids rise nearly vertically from depths of over 1 kilometer to reach the park's major hydrothermal fields. They mix with shallower groundwater flowing within and beneath the park's volcanic lava flows, which can also be seen in the photos. The ascent of hydrothermal waters is guided by faults and fractures, while lava flow boundaries control the shallow groundwater aquifers. The project closes a long-standing knowledge gap about the underlying mechanisms of Yellowstone's famous hydrothermal features. The chemistry and temperature of mud pots and springs, the eruption interval of geysers, and the unique thermophilic bacteria that live in and around those features are all well-known aspects of the park's subsurface hydrothermal features. Similarly, scientists are learning more about deeper heat sources and tectonic activity by tracking earthquakes that occur there. However, little is known about how the surface hydrothermal features interact with one another, and with the deeper sources of heat and fluids, our understanding of Yellowstone has long had a subsurface gap, Holbrook explained. It's like a mystery sandwich. We know a lot about the surface features from direct observation, and a lot about the magnetic and tectonic systems several kilometers down from the geophysical work, but we don't really know what's in the middle, and this project has allowed us to fill in those gaps for the first time. The data was collected using a unique instrument called SkyTEM, which consists of a large loop of wire towed beneath a helicopter. The loop sends downward repeated electromagnetic signals as the helicopter flies, eliciting a response from electrically conductive bodies in the subsurface. This response is recorded and analyzed later to generate detailed cross-sections along the flight lines. In environments like Yellowstone, hydrothermal fluids alter the rocks they pass through, transforming them into clay minerals, such as the surface mud pots, with increased electrical conductivity but suppressed magnetization. Scientists involved in the study were able to cover large swaths of the sprawling 3,500 square mile national park because the helicopter can travel at speeds of 40 to 50 miles per hour while towing the SkyTEM instrument, according to Holbrook. One of the dataset's unique features is its extensive coverage of this massive system, Holbrook added. Not only were we able to look deep beneath the hydrothermal features, but we were also able to see how adjacent features might be connected in the subsurface across great distances, which had never been done before. One of the unanswered questions raised by the new research is whether different hydrothermal areas in the park have distinct deep fluid sources and pathways. Instead, the park's diverse, hot spring characteristics are most likely the result of varying degrees of mixing with shallow groundwater, according to Holbrook. The project generated over 2,500 miles of helicopter lines and a massive amount of data. Following the study's publication last month, the research team made the data available so that others could conduct additional research. The dataset is so large that this first paper only scratches the surface, Holbrook added. I'm excited to keep working on this data and seeing what others come up with. It's going to be a dataset that keeps on giving. Holbrook previously worked in the Department of Geology and Geophysics at the University of Wyoming in Laramie, Wyoming, before joining Virginia Tech in 2017. In addition, he was a co-director of the Wyoming Center for Environmental Hydrology and Geophysics. I've made several field trips to collect ground-based geophysical data in Yellowstone, he said, but the airborne data covers a lot more ground much faster than we could by hiking gear into the backcountry. And with that being said, it's time to end our video. Subscribe to the channel for more amazing videos like this. We'll see you with another interesting video.